So while people start joining, I think we can start probably talking about some of the highlights of your career. You did your BSc and MSc in the Technical University of Denmark, and then you moved to the States to do your PhD. And if I am not wrong, I think immediately after, or very close after, you started your academic position at MIT, the premier engineering education institution in the world. So maybe you can tell us a bit about your journey there.
Yeah, so nothing was planned. I think I discovered what was civil engineering when I started my undergrad degree. I did not know what it was before. I did not know what was research. And I think actually I did 2 semesters of Erasmus study abroad in London, not at Imperial College though, but somewhere else. And I think that was where I was bitten with the research bug. I did not really have imagination to think that I could do a PhD anywhere outside Europe, but fortunately I had advisors that said I was a chicken if I didn't try to apply for somewhere in the States. And that led me to Johns Hopkins. And actually a week after I finished my PhD, I started as a lecturer at MIT. But a lecture is not really the same thing in the US as it is in the UK. So it's like a fancy postdoc, which I was for 2 years, and then I joined the faculty.
And as a lecturer, you are allowed to do research as well, or is mainly a teaching post in the US?
That most places it's a teaching post. I got really lucky that my position was teaching a course per semester and then mentoring some master students in their thesis work, and that became research. So it wasn't this like long-term broad strokes plans. It was, okay, we have 9 months, what can we do? But that has been really fun and really educational for me. Yeah.
Oh, yeah. And what do you think is the main? I mean, you've had a very successful career so far. What do you think is the main? Let me put it this way: if you had to advise one of our PhD students, probably that is listening here, or that is watching us, what do you think is a mark of a quality that will help you to succeed in a very competitive world of academia?
I'm going to jinx myself to say this right before I'm presenting, but presentation skills are super important, I think. And perhaps it's something that's downplayed a little bit often, that like doing the research, writing the papers, and then somewhere down the rank of list to do comes making a nice presentation, spending time on the slides, practicing what you're going to say. But I think that's actually something that should be up high, because that can really make people notice you and the work that you do. And it's not something that you're either like born being able to do or not. It's really a skill you can practice.
Yeah, I totally agree with you. I think you've picked up a very important skill that is, as you said, sometimes overlooked, right? So that's quite important to highlight. Yeah, thank you very much. And you started doing topology optimization from your PhD, or even before that?
From my PhD, yeah. So I cheated a little bit, because after I had discovered the group at Johns Hopkins and applied, I realized that there's a big group at DTU where I was. So I went over and talked to them and started playing with some of their educational papers. So I had like a couple of months of head start, but the real thing started when I arrived in the US.
And that was in a civil engineering context as well, or a different context?
It was in a civil engineering department, but it was more mechanical engineering applications, I would say.
Yeah, it tends to be, no?
Yeah. Yeah, I had this dream of coming in and designing skyscrapers with turbulent wind turbine flow, and I got talked down to material architectures. So I ended up doing something very different than what I had imagined, and then I sort of scaled back up after I came to MIT again.
Yeah. No, because it's something I think that it's a marvelous area to work on, right? Especially at the moment, and it's something that we civil engineers are not probably taking full advantage of, right?
Yeah, I think there are that with the new renewed focus on being more responsible with the construction materials, it's definitely an area that is up and coming. Structural optimization in general.
Thank you very much, Josephine. I think probably we can start with the seminar part. I think some numbers have stabilized now. So let's move on to the seminar part where you're going to be presenting your research work on freeform structural design for advanced manufacturing. I repeat for those that have joined late. Josephine is a professor at MIT, and she did her degrees at the Technical University of Denmark and then the PhD at Johns Hopkins in the US. Her research is focused on the new opportunities arising as digitalization of design and manufacturing is transforming the way we do our the way we create and build our built environment. So thank you very much, Josephine. Really looking forward to this. So the screen is yours.
Thank you, and thank you so much for inviting me. I am really excited to get to talk today to you. Those who joined the very first minute already heard, I'm not used to using Microsoft Teams, but I hope I'll be able to figure it out. I'm going to be talking about what we do in my group, and as Christian said, we work with freeform structural design for advanced manufacturing, and that is really all about developing generative design of structures. And for us, structures can really be many things. It can be something that's as big as a tall building. It can be parts or components, roofs, bricks, something that goes into a car, into an airplane, something that goes into the body, such as this inner ear implant, or really something that's as small as taking a solid and punching holes in it to make material architectures that are lightweight and high performing. When we work with developing generative design frameworks, we really work with developing the blue box in this picture here. So what we're envisioning is that for many applications, maybe you don't really need to know exactly how your structure is going to look. You just need to know what do you want from it? So how do you plan it to be supported? What loads do you plan on it to put on it? You put this into the blue box, and then the blue box gives you or generates the design for you. In order for this really to work, the blue box needs to know what happens when we take the design out of the computer. So what are the constraints and imperfections that arise when we are fabricating or constructing our structures? And is the generative design algorithm aware of it? If not, then we need to make it aware of it. And likewise, when we test our structures, what are the governing physical behaviors that we observe, and were these captured properly by the design framework? So this is like an overview of everything we do. And totally a spoiler for the rest of the talk, because this is the stuff I'm going to be talking about. But before I dive super deep into what do I mean by generative design, and what are all the the stuff that we put into this blue box, I'd like to just start by taking a step back and talk a little bit about structural optimization. Because that's what we in our group use as the driver in this blue box. So let's pretend that we're all structural engineers and that we've been tasked with building a new building. Could be on the Imperial campus, could be on MIT campus. There's lots of building going on there for sure. And we don't want this building to be the heaviest building to ever see the light of day. We'd like to optimize it a little bit. And there are a couple of ways we could go around doing that. The first way would be to use what's called informal optimization, which means that we use our past experience, we use some rules of thumb, and maybe we have some heuristic guidelines. And all of this sort of lets our design decisions be guided towards something that is better than where we started. Alternatively, we can use a formal optimization technique where we'll pose our design problem as a formal mathematical optimization problem. And we'll use like rigorous mathematical optimizers to solve it. If we decide to go with option 2, then we'll have sort of 3 categories to pick from, being sizing, shape, and topology optimization. I'm going to be talking mostly today about topology optimization, but before I do that, I'll just touch on what these 3 things are and how they relate to each other. So for our new building on Imperial campus, we've chosen that the girders have to be made by these truss beams. And we'd like to use sizing optimization to help us design these beams. So what we'll do is we'll start by choosing a connectivity. We'll put that into the computer, and the optimizer will optimize the areas of the truss and give us our design. What the optimizer cannot do for us is this cannot tell us where it's best to start. And as you are probably all aware from the case of trusses, there are many good places to start. And to figure out what is going to be the best truss for our application, we would have to try out all these different starting points. And shape optimization is similar. If we were to make a low weight beam by punching some sort of shaped holes in it, instead, we could choose a shape, optimize the features, so make the holes in different shapes. But what shape optimization cannot do is it cannot tell us what number of holes is the best one to start with. It cannot add a 7th hole, even if that is what makes all the difference in the world. And it can't add lots of holes either. Topology optimization is different in that it does not rely on this starting guess, this starting intuition of where I'm going. All you really need to know is the boundary conditions and the loads applied on your structure. Then you give this to the optimizer and ask it, where do I place material? And out comes this new design. Topology optimization has been quite popular in the automotives and aerospace industries because it's been known to lead to new and perhaps surprising design solutions that often outperform conventional low-weight design quite significantly. So in this case here, we can get a 42% stiffer beam with the same weight. And if we were to ask the question differently, how low can we go? We can get an almost 50% lighter beam with the same elastic stiffness. I don't know if this is a lunchtime seminar, but there is no such thing as a free lunch, and not in this case either. This is by far the most difficult category of structural optimization to solve. And we are left with these great looking fancy structures, but also the head scratching question of how do we actually fabricate or construct them. And I'll talk a lot more about that. But before I dive into the headaches, I'll just give you a little bit of a flavor of how topology optimization works. So we're going to be designing this cantilever beam where we have a point load at the mid of the end of the span. It has some dimensions, a height and a length. And we're going to set up the design problem as this formal mathematical optimization problem, where we are going to be minimizing the structural compliance, which in this case is equivalent to maximizing the stiffness. We're going to be enforcing a structural equilibrium. You may recall this equation from your finite element analysis. And we're going to impose a volume or a mass constraint. So we're going to tell the computer how much material can you use. And then we have to set some bounds on what the design variable values can be. Just some algorithmic details. Don't worry if you don't appreciate them. We're using SIMP to penalize intermediate densities. We're using the method of moving asymptotes in most of what I'm going to be talking about today as the gradient-based optimizer. We're calculating sensitivities using the adjoint method. And then you have to do some filtering to avoid numerical instabilities. And we're using the Heaviside projection method. This is something I'm going to be talking a bit more about later on. With that all squared off, what we're going to see now is how a design evolves from this gray, like I don't really have a clue of what I'm doing, material solution to a discrete 0-1 material or not material design. And this happens as the design is generated. Now, in setting up this problem, I'd made one more engineering decision. I had decided that this particular design would be well represented by 2D continuum elements. I could have picked something else. I could have said that a truss discretization would be more suitable, or 3D continuum elements was really relevant to my design. I think you can see that I'm getting structures that look sort of similar, but are confined to whatever resolution I'm giving the computer to work with. The methodology and everything that goes on in between is largely the same. So this is like a user specification that you put on when you set up your problem. So why am I boring you with all this? Why am I so keen about using this fancy generative design methods when I've already said that making stuff is going to be a headache? And I realized that using this clip already is dated. What I'm showing to illustrate that things are really moving in the manufacturing industry is this opening credit from the HBO science fiction series Westworld. And in this opening credit, robotic extrusion is being used to print humanoid robots. Now that is still science fiction, but this here is what's going on in research labs across the world today. Robotic spatial extrusion is being used to print. All of these examples are plastic structures. There are actually also steel examples now. One thing you'll notice in all of these images is that a lot of the designs are based on having this regular lattice that is then morphed to create an organic looking chair or structure. What we thought in collaboration with Digital Structures at MIT was that, hey, how about if we create a design framework that is actually tailored to the constraints and possibilities afforded by robotic spatial extrusion. So some of the constraints of this manufacturing process is that the nozzle can't go in a million times and print from one node, because then it's going to destroy what it's already made. As you can see, it can print free form, but it can't do so forever, because then it's going to start sagging. So we designed a truss topology optimization framework that had some of these constraints embedded. And we were able to create designs that are tailored to this new way of making. The design I'm showing here is a beam bridge that's like 2 feet, so like this big. We were meant to test it, but then COVID happened, and now it's just sitting in my colleague's office. Maybe one day. We also work with more conventional 3D printing technologies. So one technology that's really common across a wide array of 3D printing methods is what's called material extrusion processes, where you have a nozzle that moves across a 2D slice of that domain and then spits out material as it goes along. And this is used at like small scale in what's called bioprinting. You've probably all seen a fused filament printer or FDM printer in action, either in a library or in a mall or something like that. But this way of printing is also used like way up at the large scale for what's called big area manufacturing or in concrete 3D printing. We're not the first people to be interested in the intersection of topology optimized design, specifically for extrusion printing technologies. But most of the previous work have focused at the scale where the nozzle is so small that there's not really, you can really create any thickness you want. We were interested in looking more at the large scale, where if you have a design and you can force it to be relatively simple, your nozzle can only pass a discrete number of times, and so you can like make a member that's 1 width thick, or it can be 2 width thick, but it can't be something in between. Even if your design is relatively simple, right now you have to go in and you have to prepare it heuristically to fit this like discrete nozzle pass constraint. And what we really were interested in doing is moving away from that and instead create designs that are directly ready for printing. We took the basis of this in the filter that I mentioned a bit previously. So in topology optimization, you get a lot of numerical noise if you don't filter. And so it's very common practice to use a filtering approach. And we sort of wanted to take advantage of that you do this anyway to enforce implicitly the manufacturability with regards to extrusion printing. So we used a filter that's called a discrete object projection, which is based on the Heaviside method. And what this really means is that you split your design problem into a design variable space, which is the sphere in this figure where you do all your math, and then a physical finite element space where you solve your equilibrium and you evaluate your structure. And these two spaces talk to each other by the design variables being projected onto the element. So you can think of it as if you have a design variable saying go, then it's like beaming down material from space onto the earth and then creating features. In the case of discrete object projection, a filter will create 2 features, which is this like circular feature that's enclosed by a concentric ring. And classically, it's used to put reinforcement or stiff inclusions into a compliant phase. You could, for example, use this to design reinforced concrete sections where you place the reinforcement bars. We wanted to use it differently because we wanted to use it to mimic how this nozzle moves across the domain. And we made some assumption about how that works. So we said that when a nozzle deposits material, it's really creating 2 distinct regions. One red region here where you're not allowed to overlap with an adjacent pass. And then on each side of this, like a thin overlapping region where you're allowed to get close enough to something that's deposited later on. Initially, we assumed that these 2 regions had the same material properties, and we changed this filter to mimic that you'd have this core region where you don't bond, and then these thin bonding regions, showing two different directions here for the nozzle either moving horizontally or vertically. Mathematically, what you do is really you'd filter twice, one for the red and one for the green part, and then you combine that to give a stiffness of the elements in your grid. And then you just use regular topology optimization for the rest. Because it's a little bit limiting to imagine that a nozzle only prints in one direction or only prints in another direction, we added this additional design variable that determines if I'm like, what is the rotation of the nozzle. So a design variable saying go will either be printing horizontally or vertically, depending on what's the magnitude of these orange design variables. What that means is you make 3 filtering operations and combine it. But it's very similar to the case before. This here is the result that we got for the cantilever beam, and as you can see, we're really happy. It fulfills this nozzle constraint. Nothing is overlapping. Everything is within these nozzle passes, and it comes with these 2 design variable distributions. The black space on the lower left, that is telling you where am I depositing material, and you can sort of think of this as a trace for how the print path is going to be. And then this more obscure space in the orange on the lower right, that is showing how is the nozzle rotating throughout the space. Of course, we compared this to our less fancy results. We were minimizing the compliance, so a low C is good in this context. If we first compare our new design to the design on the lower left that does not have constraints on it, we see that we're losing a little bit, which is not surprising. If you ask more of the computer, like to fulfill more constraints, you're going to sacrifice a little bit on compliance. That makes sense. But what we also see is that even in this case where the post-processing or the preparation for manufacture was really simple, we're actually still doing better. And you can just imagine how maybe some structures are not that easy to interpret or may not so easily be prepared for manufacture, how much more this effect may be magnified. We're continuing to work in this direction. Some of the work that we're doing now is that we are revisiting this assumption of the 2 regions having the same properties and saying, actually, we want to be able to assign different properties to the 2 regions to sort of mimic that actually if you stack things or layer things, this transition zone is going to be weaker. We found that having just 2 directions to design with was quite limiting. So we have implemented multiple directions. It works the same as before in this orange space, that it just has more to pick from depending on what the value is. And these here are some preliminary results, so please excuse the coarse mesh. This result here is a cantilever with 3 directions where the bonding material and the core material has the same stiffness. And we have obtained also for comparison a result with half stiffness in the bonding region. And you can see they differ. There's less stacking going on in the blue version of the design. Actually, the bonding region, the amount of bonding material placed, is a little bit bigger in the blue design. I'm just going to call it that. not a lot, but a little bit, but it's placed more smartly. And the reason I feel confident saying that is because we tried to compare the two designs. We couldn't just compare them as they came out, because that's not really a fair comparison. They don't have the same material properties. So we did a sweep. We analyzed the two designs with varying degrees of stiffness in the bonding regions. And what we could see was that actually the design obtained with a lower stiffness in the bonding region outperforms our stiff design in all cases that we tested. It's not necessarily true for all obtained designs, but it's a clear trend we have seen in what we're working with. So now I've talked quite a lot about topology optimization specific things. I've talked about how you can tailor topology optimization to the design of structures that are made in a particular way, made with some 3D printing mainly. But since this is a structures seminar, I really want to talk a bit about topology optimization for civil structures and how there are plenty of opportunities in that space as well. Because manufacturing is also advancing in the civil structure space. And it's not just advancing by creating new 3D printing technologies, it's also advancing by more digital ways of CNC carving, of making formwork and etc. So one example of something we've worked on, which I want to talk a lot about, is the design of interlocking timber joints. Interlocking joints have been around for thousands of years. And when you look at the historic examples, they're quite different, but they're really all governed by how good are you with a saw and a chisel. I'm not that great at a saw and a chisel, but I know how to operate a CNC carver. And so that really has opened a realm of possibilities of what sort of shapes are available for making joints that come together and lock each other and can potentially even be disassembled again. I alerted a little bit to this before we started, but in the context, the global context that we are in currently, I think we as an industry, a civil engineering industry, sort of have to start to live up to our responsibility in terms of the global CO2 emissions produced by our sector. So if we look at the annual global CO2 emissions, building materials and construction is 11% of the global annual emissions. And contrary to almost all the other pies of this chart, this is a growing pie because of urbanization, increase in population, and the fact that we haven't paid a lot of attention to it. One way that we can estimate if we're going to be making a new structure, how much is going to be the embodied carbon impact is through the global warming potential of the structure. And this is really actually quite simple to calculate. You just go through all the elements in your structure, you get the weight of the element, and then you multiply it by this embodied carbon coefficient of the material that it's going to be made of. And once you've been around your whole structure, summed everything up, you have this global warming potential. So if we want to be cautious of how much material we're using, or how much we're impacting the planet when we're building, if we're just building with one material, it's actually really simple, because then we can just worry about what is the weight, the gray part, and we can minimize the weight. And if we minimize the weight, then we're also going to be minimizing the global warming potential. But if we have a structure that has more than one material, and these materials have very distinct embodied carbon coefficients, then it's not that simple. then it's not necessarily just minimize the weight of everything. To illustrate that, we've worked on a timbered steel truss framework where we have looked at minimizing the embodied carbon. This picture here is from the University of Massachusetts Amherst, their design building, which is in one of the first mass timber buildings in the US. Of course, we started out by looking to literature, and we found that there was surprisingly little optimization of multi-material trusses, and specifically topology optimization of multi-material trusses. And then when you do truss topology optimization, which is what we were looking to do, you often start, or at least we do, with this ground structure where you have a lot of potential elements, and then in classic truss topology optimization, you size each of these elements and you let some of them go to zero, the area of some of them go to zero, which leaves you with your truss structure. And what we wanted to do was to add this decision variable that says, okay, in addition to figuring out how big it has to be, you also have to determine if I should be timber or steel. That gave us a problem formulation initially that looks like this. We again maximize the stiffness subject to an equilibrium constraint. We have some bounds on the design variables and a volume constraint, actually a weight constraint or a global warming constraint. We tried with the two to compare. And this X variable, just again, it picks if I'm putting material 1, which is timber, if I'm 0, or if I'm putting material 2, which is steel when X is 1. And to like determine the properties between the two, we used like SIP functions that we know from continuum topology optimization. So these are the ground structures we started with in 2D and in 3D. And at first we employed a weight constraint. And we got these all steel structures. We switched out the weight constraint with a global warming potential constraint, and we got almost the same all timber structures. The student who was working on this was like, this is a bummer. But then we looked at it, and it's a good thing, because steel is about 30% stiffer per kilogram weight. So if you're want to create a stiff structure and you're worried about weight, then steel is the material to use. On the other hand, timber is about 160% stiffer per kilogram CO2. So if you want a stiff structure that has a lower global warming potential, then you want it to be all timber. It's going to be heavier, but you want it to be all timber. To really be able, this is sort of idealizing the materials and not worrying about some relevant constraints. So we wanted to elaborate on it further and decided to aim directly for minimizing the global warming potential and employ some stress constraints, where these stress constraints, of course, differ. So there's one set of constraints that's relevant to steel, and one set of constraints that's more relevant to timber. So we had to be able to formulate the constraints so that they could vary with the X parameter. I want to say with this is one of the only times that we're not using MMA, but we're using the FMINCON optimizer in MATLAB, and we're calculating the sensitivities using direct differentiation. These here are our designs, where we were able to obtain these hybrid structures, where we have timber placed in the compressive regions, steel in the tensile regions. And if we compare this to the all steel designs, then we were able to improve the global warming potential for around 10% for all cases. This is not quite an apples to apple comparison. I don't think it's fair, because we're not really including buckling, which would be a bigger problem for steel than for timber in compression. So I think if you were to design it for real use, the actual gains would be even bigger.
أنا أسمع على
I want to move to talk a bit about topology optimized design for the biggest sinner of them all in terms of construction material, which is reinforced concrete. And this is going to be the last topic that I'll touch on. So when I say that concrete is the biggest sinner of them all, I think partly of this plot here that shows what the OECD estimated was the construction materials that were used globally in 2017 and what they think is going to be used in 2060. And on the top of this chart, we have sand, gravel, and crushed rocks, which are all the ingredients you need to make concrete. Why this is problematic is because cement, the glue, has a very high CO2 impact. It's estimated that the global annual contributions of cement alone is about 8% of the global emissions. So while of course there should be research on creating green cement, we just wanted to ask the question if until we get to that point, can design contribute? Can we just use less concrete in reinforced concrete structures and design our way into getting structures that does the same as what we accept today, but just has a lower impact by virtue of having less concrete? We started this work out again by looking to literature and recognizing that you could really do rather fancy things computationally. There are very few examples of things that have been constructed. There were in 2017 no examples of experimental validation. And so we thought we'd start there. We started by looking at plain concrete beams that we cast into CNC milled formwork. We tested our beams and found that the modifications that we had to do in order to manufacture them actually in some cases were very detrimental to just building back on all that nonsense I talked about in the beginning about how important it is to be able to capture the constraints and imperfections associated with manufacturers really manifested itself. We then proceeded to look at reinforcement, and we designed strut and tie layouts that we laid into prismatic beams. One very encouraging thing to come out was that complexity does not actually add anything. So when we compared a standard by hand designed to topology optimized design with varying levels of complexity, we saw that in terms of stiffness, using topology optimization gives us a boost, but going complex doesn't give us more than that. And we could see that even more clearly when we looked at the normalized load capacity. Using topology optimization is going to add about 20%, but you don't have to go complex because that doesn't necessarily give you anything beyond that. An interesting thing about these models is that when they come out of the computer, they look like this. They have these black regions where you have the force flow in the concrete. And then you have the red, which is the steel layout. But when you make it, you just make a prismatic beam anyway. And that's even though these white regions in the computational model, at least, they're not really contributing. They're not carrying load. So our question was, can we just not put material there? We looked at a simply supported beam, and we knew that there were going to be some obvious problems like steel coming in and connecting in a one node with concrete. Like that's not going to work physically. So to just avoid some of the most obvious problems, we decided to just try to remove 25% and see if that was possible. That gave us a design that looked like this. We compared it to a design that we created by hand, and a design as it's meant to be, so with 100% concrete in a prismatic beam, and then the reduced concrete design. We don't have a massive lab, so we have water jet cut the reinforcement from steel plates in order to make prototype sizes. We cast them into the beams, gave us these 3 different beams to compare. We tested them in the lab, and we got these results where we're seeing the stiffness of the 3 beams. Murphy was in the lab that day, so I can't say anything about the ultimate strength with any confidence, at least. So what we're seeing here is, again, that if you go from standard to using topology optimization, you get a boost in stiffness. And what we then see moving from center to right is that, of course, taking out concrete does something. Like, it has a cost. It's not for free. We're lowering the stiffness again. But the encouraging thing in this graph is that actually we have a pretty identical stiffness of the standard that we accept as good today, and the topology optimized that has 25% less concrete. So this is an area that needs more investigation, but yeah, maybe it is possible to remove significant chunks of concrete and still get the performance that we accept today. With this, I want to wrap up. I hope that I've convinced you that topology optimization can be used to design structures on scales really ranging from material architectures up to reinforced concrete structures. I've also tried to convey, at least, that post-processing should, as much as possible, be avoided, and constraints should instead be embedded into the design framework to just limit the need for errors that incur as you translate your design from the computer and out to the real world. For civil scale structures, topology optimization can also be used in various ways to reduce the embodied carbon. We've seen that for timber steel trusses, we get lower embodied carbon when compared to single material structures. And what we've seen that's very encouraging for reinforced concrete is that we don't need to go highly complex in order to get performance improvements. I've said we is myself, it's my collaborators, Ernest Ching, Jan Louis, Jackson Jewett, Leora Honey, Yiyang Huang, and Caitlin Miller up from Digital Structures. We could not have done any fabrication or testing without the help of Stephen Rudolph and Christopher Devat. Very few things can be done without funding, so I'd like to thank NSF and the MIT Center for Additive and Digital Advanced Production Technologies. And with that, I want to thank you for inviting me. Thank you for your attention, and I look forward to answering any questions you may have.
Thank you. Thank you very much, Josephine. Fantastic presentation. Really, really, really fantastic. For the questions, I think if you don't mind raising your hand, so I can give you the I'm sure you, or you, if you don't have your phone, you maybe you can also place your question in the chat, and I'll read it aloud. So George, please, can you unmute yourself?
Hello.
Yes.
Hello, am I audible?
Yes, I can hear you.
Yes. Firstly, I want to thank you, ma'am, for such a wonderful presentation. It was very insightful. So I am actually doing my major project on optimal design of truss and shell structures. So the question I wanted to ask you was about the nodal constraints. So during the additive manufacturing, you told that there will be a because when we include the nodal constraints, there will be a lack of stability, like not stability, the stiffness actually. So doesn't it mainly happen at the connections, the joints?
Can I ask if you are referring to the robotic extrusion or the I'm thinking you're more interested in the robotic extrusion with what you're working on. Yeah.
Yes.
So we didn't go about incorporating it in a very sophisticated way, which you totally can when you're working with trusses or frames. But we just when we started with the ground structure, we just started with a ground structure that didn't have more than a certain number of members going into one joint. So it was never possible for the optimizer to place 10 members into a joint where we only wanted 4 to connect. You can also add it as a constraint where you say, if things are turned on, then I only want 4 of them to be turned on in each node. I hope to publish something on that in the future, but we haven't gotten that far yet.
Okay. Can I ask whether when we consider it with the continuous design variables, won't it be a better way to make a stiffer structure than a discrete model for optimizing?
So I think in my experience, if you're thinking about trusses again,
yes.
Yeah. So in my experience, that is true if you have larger volume fraction structures. But if you go down to very, very low volume fractions, say you have a big design domain and you only want below 10% of material in it, in my experience, the continuous design variables are not that great at navigating that space. And I think we need to talk to our colleagues in math about how we can better solve that kind of problems. But yes, if you have like more than 20% material to play with, you give more design freedom, and then you can use gradient-based optimizers so you can navigate with less computational effort, and that tends to allow you to identify better solutions.
Thank you very much. Stanislav, you have a question?
Yes, thank you for the presentation. It was very interesting to listen. And I have a few questions, if you don't mind. So can you clarify for me, when you were considering trusses, was the analysis done with linear elements, so no nonlinearity included?
Yes, we use linear elements.
Okay, so did you try something with nonlinearity, like geometric nonlinearity or material nonlinearity, specifically for concrete?
Not so. We've tried for concrete putting stress constraints that were nonlinear, so putting Drucker-Prager constraints, still wanting everything to remain in the linear region, but just not exceeding into to plastic deformations. Mm-hmm. When you do concrete by itself, our experience is that that's difficult because there's such a big difference in tensile and compression capacity. I haven't tried doing it with both concrete and reinforcement, but I think that's like lots easier than doing clean concrete.
Yeah, thank you. I have 2 more questions, if that's okay. So I was dealing with like sort of topology application in my work, but we were dealing with nonlinear problem. And what I found is that when you have filters on top of filters, which we're describing for your case where you have several orientations, that derivatives, they become very sensitive to minor variations and become very unreliable as you go with it. Did you face the same issues, and how you dealt with them, if you did?
So in my previous work, I've definitely faced issues like that. I want to say for the print stuff I showed, it's surprisingly insensitive to, like, you can get away with changing things quite a lot without it destroying everything. But in general, I think that is a true statement, what you're saying.
Yes. Yeah, and then the last question, which basically stems from the previous one. So I was also using MMA and the SIMP algorithm, and what I found is that they are very local solution prone. So they can converge to a local solution that might be very, very close to what you originally started with, while there definitely exists a better solution. Did you create some kind of method to kick it out of that, or just multiple tests with different starting solutions?
Yeah, so I think that's a known problem, and I would recommend you to read a paper by Stolpe and I forgot her last name, Mariana something, where they investigate exactly that and come to the conclusion that maybe MMA is not always the best way to go. But there are historic reasons why it's good to demonstrate your work with MMA. But that's a very known problem, and if you insist on using MMA, I definitely concur with you that trying out different starting points is a good idea, and that is even more the case if you have something that's very nonlinear, so with a lot of filters or it have nonlinear mechanics inside it.
Yeah, thank you.
Thank you very much. We have a very quick question from Peter.
Right. Thank you for your presentation. It was very interesting. So when we talk about design optimization, one issue that comes up quite quickly is the fact that our limited understanding of both structural and material behavior could stand a stumbling block in the adoption of optimized structures. For example, to your talk, when you showed where you use timber and steel composites to improve on the global warming potential of the structure, that to me is very interesting on paper, but I wonder whether our limited understanding of how that kind of composites would behave could stand a stumbling block in its adoption. I wonder what your thoughts on that would be.
Okay, so that's a very interesting question. I think that there are many issues that block adoption, and what I don't think the one that you're saying is necessarily the biggest one. I think a big issue is confidence in the solutions, confidence in the technologies, and also confidence by the users. Like how would you feel if you walked into something that didn't look like the structure you're used to, or was built with some elements that look very different from what you've been used to employing for the last hundreds of years? So I think that might be an even bigger limitation, is that engineers have to feel comfortable with the solutions, and the users have to feel like we're still safe even though we're using less material. But I will always encourage that you should check, like do all the validation checks that you are normally doing. You can design with uncertainty as well. There are other people than me that are working on it. I think you get a noisy problem if you put everything into one, but it can be done. But there are definitely many barriers for adopting or accepting solutions that are optimized.
Right. Thanks.
Thanks a lot, Josephine. I think a lot of people will have more questions, including me, but time has passed very quickly. Fascinating stuff. And thank you very much for delivering this seminar to us.
Thank you for inviting me. It's been a pleasure.
Yeah, thanks a lot. Bye. I'll be in contact with you later. Thank you very much. Bye-bye.
Just have to figure